Swayam Prabha. Digital India. Educated India.
So now I'm going
Thank
to.
you. Thank you.
So I'm going to introduce then the next speaker. So our next speaker is Mr. Ramanan from Indian Institute of Technology Madras, and he's going to make a presentation on modeling energy transitions, assessing technologies and critical influencing factors. So please try to keep the time.
Good.
Thanks very much.
Yeah. A very good afternoon, ladies and gentlemen. Today I'm going to present on modeling energy transitions, assessing technologies and critical influencing factors. So here we consider a case of green hydrogen pertaining to a state in India. So the overview of the presentation is as follows. Introduction, hydrogen production routes. We discuss on hydrogen production routes and some utilization priorities, and also delve into the Indian context of how the green hydrogen can evolve. And we then discuss on the motivation, methodology, and solution framework. Further, we move on to the case studies pertaining to a state in India, and then discuss scenarios based on key influencing factors and their summaries. And finally, we discuss conclusions and projected future works. So we have 4 different ways or recipes through which hydrogen can be produced. So there is a brown hydrogen which involves production by coal gasification with no CCS or carbon capture sequestration technologies. There is gray hydrogen which is production through steam methane reforming with no CCS technology. Blue hydrogen involves production by either of the above 2 processes, but it also involves the carbon capture technology in place. The green hydrogen is the production by water electrolysis using electricity, basically the renewable electricity sources, and it is produced, the oxygen is vented with no negative impact. So then we move on to the clean hydrogen utilization priorities. Here we see that hydrogen can help tackle various critical energy challenges. It offers ways to decarbonize a range of hard-to-abate sectors like iron and steel, chemicals, mobility, etc. Hydrogen can also be transported as a gas by pipelines or in liquid form by trucks, rail cars, and ships, much like liquefied natural gas. There are, though, critical bottlenecks in place. Producing hydrogen from low-carbon energy is currently very costly. Also, presently, hydrogen is almost entirely supplied from natural gas and coal, which are fossil-based sources. From the Indian context, we see that there is about more than 7 million tons of hydrogen that was used in India in 2020, with about 45% used for refining, 35% for chemicals, and 20% for iron and steel production. All of the hydrogen demand was met through domestic production based on fossil fuels, with natural gas accounting for 3/4. India has high capability for producing hydrogen from renewables at low cost because of its tropical climate. And hydrogen production from renewables is estimated to just cost about 1.4 to 3.5 US dollars per kg of hydrogen, comparative with production through unabated fossil fuel methods. So next, we move on to the motivation of the talk. We see that to understand the role of green hydrogen, we need to analyze the hydrogen utilization priorities among the key hard-to-abate sectors. We also need to assess how techno-economic and environmental factors influence the transition. So here we include technology investment decisions of switching to green hydrogen from existing fossil-based technologies. Also, we need to take economic decisions considering the price of green hydrogen and also various factors involving the environmental impacts. So next, we also need to address the need for supply chain level mapping involving production, consumption, as well as the logistic segments. This involves integrated analysis at the system level that is required to design efficient infrastructure for producing hydrogen and transporting it to the end users. So here we propose a 4-fold methodology. First is to perform plant-level spatial mapping of potential supply and demand locations. Next, we capture supply chain dynamics through supply-demand balancing based on the end users as well as the producing sites. Then we need to evaluate technology switching opportunities of the end users through techno-economic and environmental factors. Finally, we identify the most feasible mode of transport for the end users, that is either road or rail from the supply sites to the demand nodes. So here we choose agent-based modeling strategy of the green hydrogen supply chain. Professor Widodo in his previous talk had mentioned about the use of resources and actors in the supply chain. So that is what is considered here. So each of the agents are actors. They have rational decision making in place. So we have hydrogen suppliers, logistic providers, end users, and environmental regulator has the agents. Where we see the supply chain that has been considered in the model, we have the solar, wind-based renewables, and water electrolysis is the process considered. There is also storage in green hydrogen spherical storage tanks. This green hydrogen is then transported through liquefied hydrogen trucks or rail cars to the various consumers like refineries, fertilizers, iron and steel, and also mobility. So this is the overall schematic of the hydrogen supply chain that have been considered. Here we have a number of suppliers which has been indexed as P, and we have a number of end users and that have been considered: fertilizers, refineries, iron and steel, and many more. And each of the fertilizer has a population of agents starting from 1 and indexed to N. And we also have roadways and railways as the logistic providers considered in our model. So you can see that the hydrogen suppliers, this involves a material and information flow diagram. The hydrogen suppliers supply H2 to end users. The end users also need to choose on the logistic providers, whether road or rail. And this has been constrained by environmental regulations in place. There are also 4 sub-agents inside each of the end user. And those include commercial, strategic, procurement, and operations. The commercial sub-agent estimates the fuel demand and passes it on to the strategic sub-agent, which then chooses the technology. Then this is passed on to the operations to operate based on the technology, and the procurement agent kind of identifies what supplier to procure the hydrogen from, as well as to identify what will be the mode of transport to procure the hydrogen. So here we model the techno-economic and environmental factors considered in the model. We have green hydrogen technology switching cost, emissions generated per unit energy across the various industries, as well as potential green hydrogen consumption based on energy requirement as the 3 technical factors. We have considered green hydrogen prices, and we have to consider uncertainty in the prices, and that's what we see in the scenarios next. And we have logistic transport operational tariffs also included for both road and rail. And we have carbon pricing, which is, we consider 2 different carbon pricing schemes, which is fixed as well as escalating scheme for the next 2 decades. And we also have emission limits, which can have a check on how much of emissions each of the hard to abate sectors can emit. And H2 supply chain, we have considered here on Tamil Nadu case study. We consider 3 locations in Tamil Nadu having high potential for tapping renewable energy for production of hydrogen. 3 of them include one at Neyveli, one at Kamudi, and one at Muppandal. And these 3 are located at 3 different directions in Tamil Nadu and are producing solar as well as wind farms. So end-use sectors we have considered are fertilizers, refineries, iron and steel, cement, chemicals, and transport and distribution. This model has been implemented on a tool called AnyLogic, which is a business simulation tool. So here we consider a spatio-temporal representation of the model, and the strategic end-user switching decisions is being depicted. As we see, we have considered a lot of end users, and these have been mapped in the plot that is depicted to the right. And there are about 3 green hydrogen supply sites that have been mapped. One at, as already mentioned in the previous slide, one at Kamudi, which is in the central Tamil Nadu, and also at the northern coastal in Neyveli and others. So here the end user gets the end product demand, and these are made, the choice of technology is being made based on green hydrogen availability, switching and delivery economics, and environmental regulations. So based on these factors, it then decides to whether change to a newer technology, which is the green hydrogen, or continue with its existing technology. And this decision is being made iteratively annually. So here we monitor the scenario description. We have 3 different cases of economics considered. That is a rapid price moderation case, gradual price moderation, and slow price moderation. In the rapid price case, we have the hydrogen price reducing from $6, which is at present, to $1.1 by the next 20 years. And in the gradual price moderation, we have $6 reducing to $2.2. And in the slow price moderation, we have $6 reducing to $3.2 on a more protracted way. The carbon pricing have been considered as fixed and escalating. So the fixed carbon pricing includes a $20 per ton CO2 emitted throughout the simulation horizon. And escalating, we have a $20 per ton CO2 emitted at present, and with a 10% year-on-year growth, reaching about $50 by T is equal to 10, which is, say, if it's 2021, it will be 2030. So we also considered environmental regulatory limits considered for illustration. So 3 sets. Set 1 of scenario includes the 3 economic cases without carbon pricing and environmental regulations. Set 2 includes the 3 economic cases with escalating carbon pricing and without any environmental regulations. And set 3 will actually project the 3 economic cases with both escalating carbon pricing as well as the environmental regulations in place. So here I'm going to play an video where you'll see how the logistics as well as the transport segment evolve over time for the 3 different cases of economics. So this has been simulated for 20 years, and each simulation takes about 1 year of operations. So what we see is the dotted red lines denote the evolution of transport of hydrogen by road and for the distribution and transport sector, while the dotted orange lines that evolve over time denote the same by rail. Similarly, the brown lines represent the evolution of transport for the various industries by road, and for blue lines denote the same by rail. And this has been modeled based on the supply and demand balancing. So now we move on to the scenario inferences. For the interest of time, I'm not delving deep more on the results, where we have a detailed results segment. So here I just project the summary of the results that have been obtained. For the rapid price moderation case in the set 1, we see that it is conducive and helps realize a significant market penetration of hydrogen after T is equal to 10 years. And about 3% hydrogen is utilized by T is equal to 10, which further grows to 60% by T is equal to 20 from the start of the simulation. Transport and distribution, fertilizer and refineries are the major consumers after T is equal to 10 years. And for the gradual price moderation, it results in an uptake of hydrogen only in the transportation and distribution sector. And about 1.3% hydrogen is utilized by T is equal to 10, which further grows to only 2.6%, which is double the actual consumption by T is equal to 20 years. In the slow price moderation, we see similar outcomes as the gradual price moderation is realized. For the next scenario, set 2, we have economic cases being considered, all of them, with escalating carbon pricing but with no environmental regulations. So what happens when we impose the escalating carbon pricing policy? So in the rapid price moderation, there is a significant increase in uptake of hydrogen. We see that fertilizers, refineries, iron and steel, cement and chemical plants, all of them switch to hydrogen. It is about 5% of hydrogen utilization by T is equal to 10 years. So there is a very lesser growth that has been estimated for the next 10 years, but it gradually grows to almost completely by subsequent 10 years. And for the gradual price moderation case, we see there is slight increase in uptake of hydrogen after T is equal to 15 years, which is like amounts to about 1.3% hydrogen utilization realized by T is equal to 10, which further reaches to 60% by the next 20 years. In this case, we see that transport and distribution, fertilizers and refineries are the major consumers, switching after T is equal to 15 years from the start of the simulation. For the slow price moderation, we see there is a marginal increase in uptake of hydrogen. Only in 2040, there is not much hydrogen uptake for the next 20 years. And about 1.3 hydrogen utilization is realized by T is equal to 10, which further grows only to 6.5% by T is equal to 20 years. And very few plants from iron and steel really switch to hydrogen. This is the third scenario set where we consider all the 3 economic cases with both the escalating carbon pricing and environmental regulations. So we see that while we impose emission caps with both escalating carbon pricing, we see there is an immediate increase in the uptake of hydrogen. Cement plants, which are basically hard to abate sectors which emit a lot of emissions, so switch the earliest due to higher emissions, while fertilizers, iron and steel and refineries follow after T is equal to 6 years. Chemical sectors also switch in the rapid price moderation case. So there is about 100% hydrogen utilization that is being realized in the next 10 years in the rapid price moderation case, while it reaches to 98.3% of utilization in the gradual and slow price moderation cases in this scenario set. So overall conclusions, we see that in the case of economics driving the transition, the rapid price moderation case is the most favorable for transition to hydrogen-based economy. While we include the carbon pricing policies also, we see with the fixed carbon pricing, it does not result in bolstering the transition any further. There is also no significant market penetration of hydrogen in the long run. While we move into the escalating carbon pricing, we see that it enables a gradual transition to hydrogen-based economy in the latter part of the decade. And though economics must remain favorable enough for the transition, When we impose environmental regulations which are more stricter, we see that it is found to be extremely beneficial both short term as well as in the long run. And high emission industries are forced to switch to hydrogen because it is an environmentally benign fuel when it's produced from renewable energy sources. So as future work, we plan to expand the model to include pipelines as well as a mode of transport, as well as marine mode of transport. And we also currently there is no supply caps in considered in our model, and how I plan to include constrained supply based on availability of electricity as well as a clean water for producing hydrogen. Thank you.
Thank you very much. So you keep the time, so good. The floor is open to questions. So we will upload afterwards. Yes, first answer the questions.
Yeah, thanks for the presentation. So I was going to ask a question about cap, but you mentioned that it's part of your future work, because really the benefit of agent-based modeling is when you have competition and the prices may actually rise. So maybe I'll ask a different question. So did you consider the contracts? So if I am a supplier or a contract between supplier and a consumer, how frequently can it change? So today I'm buying from someone, can tomorrow, if something gets better, can I switch very easily?
Yeah, so based on the pricing, because here each of the end users make a decision rationally. So I mean by end user, not the sector, but each of the individual plans in the sectors. So each of them make a decision for procurement and logistics as well as for switching. So if a supplier is kind of not feasible enough to procure hydrogen from, then they can take from another supplier. But again, we have also estimations of the logistics transport as well as the pricing of hydrogen in consideration in the model. So that is possible in the model framework.
The duration of the contract will have an effect on the feasibility.
Correct.
So just a comment.
If it is a long-term contract, that might be possible. So we can include all the different types of contracts, maybe the short-term as well as the long-term contract.
Okay, I'm going to take another question there.
Hi, Ramanan, thank you. This is Professor Satya here from Applied Mechanics, IITM. So in the scenarios you're modeling, so there is this whole construct of $1 hydrogen. Now, are there any scenarios where you would find that $1 hydrogen is not economical? For example, the power that goes to producing hydrogen might find a better offtake than going to hydrogen. So do you see any scenarios where in this modeling framework that can never be achieved?
So if you see the rapid price moderation case is the one where we see $1 hydrogen that is happening by, say, in the next 20 years. So that might not be feasible enough in the long run, but we have considered that in our scenario as well, so that to check whether what will be the outcome of the model. But we see that there's a lot of hydrogen uptake in kind of in the latter part of the next 10 years. Yeah.
Okay, just a small follow-up question. What needs to happen for that scenario to become true? For example, what needs to be other forcing mechanisms, maybe some conditions on the power offtake, or is there any forcing mechanism that will make sure this $1 hydrogen happen?
So I think we should have environmental policies in place. So when we have stricter environmental policies, eventually there will be a lot of uptake of hydrogen in the near run, and that will have a technology impact of switching of hydrogen taking place closer in the next 5 or 10 years. So I think that might be the answer. Yeah.
Thank you.
Okay, thank you. So I propose that we switch. So first, thank you very much. So
Thank you.